Arrhenius equation. It is an equation which relates temperature and rate constant. And we know that rate constant is directly proportional to rate of a reaction. Well, Arrhenius equation not only relates temperature and rate constant, but temperature and rate of a reaction too. The Arrhenius equation is K is equal to A e power EA capital EA upon RT, where K is a rate constant. K is a rate constant and A is a frequency factor. Frequency factor. It is also known as a pre-exponential factor. It indicates the number of effective collisions. These are the collisions which convert the reacting molecules into product in a reaction. And capital EA is an activation energy. Activation energy. R is a gas constant and T is a temperature. Well, this equation can be simplified, and to simplify this equation we can take ln, that is the natural log, on both sides of the equation, and the expression we get ln k is equal to ln bracket a e power capital EA upon RT. Well, we know that ln x into y can be written as ln x plus ln y, and we apply same concept over here. As a result, the expression we get ln k is equal to ln a plus ln e and powers capital E A upon RT. Well, ln and e will cancel out, and here's the expression we get ln k is equal to ln a, and here we have minus EA upon RT. Well, this is the Arrhenius equation in simplified form, which can be used for a reaction which is taking place at a particular temperature, at a certain temperature. And if the temperature, activation energy and frequency factors of a reaction is known, the rate constant of that reaction can be calculated. What if the reaction is taking place at two different temperatures, or in other words, if the temperature of the reaction is changed and its rate constant will also be changed. We assume that a reaction is taking place at certain temperature and its temperature is changed. Assume that the initial temperature of the reaction is T1, and when it is changed, it becomes T2. And as a result, the rate constant of the reaction will also change. The initial rate constant at T1 temperature, that is the initial temperature of the reaction, is K1, and when the temperature changes, rate constant of the reaction also changes. It becomes from K1 to K2 respectively. Well, here we have different variables from T1 to T2, K1 to K2. So as a result, we get two different equations. We can plug in these variables one by one. So here the expression that we get for initial temperature and at initial rate constant, the expression we get, yes, we have ln K1 is equal to ln A remains constant when the temperature of the reaction is changed, and here we have EA upon RT1. We label this equation first equation, and for the final temperature, the expression we get ln K2 is equal to ln A minus EA upon RT2, and we label this equation second. Well, to get a single equation for a reaction which is taking place at two different temperatures, we can subtract the first equation from the second one, and so that we can get one uniform equation for a reaction taking place at two different temperatures. So here subtracting first from second equation. Here we have ln K2 minus ln K1, and since we are taking ln K2 first, this expression will be written here on right side, ln A minus EA upon RT2, and then we have this expression, we use bracket minus ln A, and see here we have EA upon RT1. Now we can simplify this expression further. We open the bracket, and yes, we get ln A minus EA upon RT2 minus, and we remove the bracket, we get ln A, and minus minus become plus EA upon RT2, and on left side we have ln K2 minus ln K1. ln A minus and ln A plus cancel out, and I write the positive variable here. First EA upon RT1 and minus EA upon RT2, and on left side we have same setup, and so you can see in both the fractions we have EA upon R, that is common, so we can take EA upon R as a common, and so we get 1 upon T1, bracket 1 upon T1 minus 1 upon T2, and on left side the expression we have ln K2 minus ln K1, and we know that ln x upon y can be written as ln x minus ln y, and we apply the same concept over here. As a result, we get ln K2 upon K1, and on right side we have EA upon R 1 upon T1, and here we have minus 1 upon T2. This is the Arrhenius equation, which can be used for a reaction which is taking place at two different temperatures, and so the rate constant are also different of that reaction. And in this expression, if you look at, you will find that you see that activation energy, this is EA stands for activation energy. Activation energy is inversely proportional to rate constant because it is K2 upon K1. If it is K1 upon K2, we can say that it is directly proportional to, but if it is given here K2 upon K1, that's why EA is inversely proportional to rate constant. It means that if the value of activation energy is smaller, the rate constant value will be larger, and as a result the rate of reaction will be faster. And here we can say that if the value of activation energy is larger, the rate of reaction will be smaller.